Today we're going to talk about how we managed to extract a probabilistic, deterministic, finite automata from a recurrent neural network, which we trained on locally sourced traffic data from this junction that you can see on screen in Bergen. And the goal of our project was more or less to see if we could extract a PDFA, which will explain what it is. And if that PDFA could tell us something about what the recurrent neural network is learning. And so we'll now go into some of the things that you need to know. Sorry, we have some technical issues here. Okay.
Oh, fuck.
So we started at the wrong way around. All right. Here we are. Okay, sorry guys. So these are the three things that we'll have to go through before getting into some of our results. And the primary thing is the extraction of a regular DFA, which is a deterministic finite automata. And we'll talk about the extension of this DFA, which is a probabilistic extension of that. We'll then go into that relationship with the language model recurrent neural network. And then we'll go into our results. So the junction on screen here is where the measurements have been taken. We'll explain the data set further on. So primarily, let's look at a deterministic finite automata. And more or less, for those of you who are unfamiliar with it, it's a set of states and a set of sequences that together with an alphabet define some language. And that language also defines some legality. And so we'll start at these three sequences here, A, B, and C, that are states. And the initial state is A, marked by an arrow coming in. And to define the legality of a given input sequence, you would need to follow the sequence in the DFA and look what state you end up at. And so we'll just do some test sequences to understand the basic principle. The first sequence could be only 0 and then 1. So you'd follow the transitions going through 0 and 1, and you'd end up at this state called B. And this state we've marked as gray, defining that that is a legal finishing state. You could also do, for example, 1, 1, and then 0, and end up at C, which would be a non-legal finishing state. So this is the basic idea of DFA, and extracting that is done by following Dana Anglin's lstar algorithm. And in this lstar algorithm, we assume that there is some oracle, and that oracle is an all-knowing entity. So we can use the oracle to get some correctness. And so we pose questions to it. And these questions are either membership queries, which is members of some sequence. So we could ask, is AAA a legal sequence in the DFA that we are after? And you could get yes or no. You could also ask an equivalence query. So for example, is the DFA that we drew in the last slide, is that the correct DFA? And if it is not, then the oracle can give you some counterexample. And so it keeps an observation table of these membership queries so that it can learn whether or not it's correct.
And so, yeah, like Halvor said, the lstar algorithm basically interacts with this oracle, which contains some DFA that we want to learn. And it poses the membership queries and equivalence queries to build up this table. So for example, this DFA will make the lstar build up this table. So let's look at what this means. So if you look at the prefix sequence here, which is the index here, the lstar essentially goes to some state defined by the sequence. So for example, if you look at this sequence here, 1, 0, let's go to this state, 1 and then 0. We are now at the 0, 1 state. And it'll firstly ask, what happens if I just stop here? Is this a legal state? The oracle will return 0 because this is not a legal state. And it'll also try some other sequence from this state, for example, 0. And then let's go here and to 0 to 1, which leads us to a legal state. The oracle will return a 1 for it being legal. So the key insight here is that if the sequences around some state is equal to the sequences around some other state, have the same legal sequences, we can say that we know that we will find that the states are equal. So for example, it has found that the state here, 1, is the same state as the state reached by sequence 1, 0, 0. So the same state reached by 1, if we go here, is 1, 0. And the state reached by going 1, 0, 0, 1, 0, 0 is also the same state. This over here is simply some more entries defining the next state reached from some state. So let's look at this state here, reached by 1, 0. It'll define that going 1 will lead us to 1, 0. And so basically this table has everything we need to build up the DFA that the Oracle contains.
And so from this, we needed to find a probabilistic extension because we wanted to find the probabilities of certain events. And so PDFA or probabilistic DFA is more or less an extension that allows for chance prediction. So based on what current state you're at, we can look at this initial state here. The number inside is the end token probability, marking instead of the legality of that being a finishing state, it is what is the chance that this is the state that we end up at. And it also has 2 outgoing transitions, which has a token, which is A or B. And that token also has a probability, which marks, given that we are at this state, what is the probability that we will move through this token? This is also closely related to language model RNNs. Oh. There you go.
Yeah. And so a language model RNN is simply an RNN coupled with a next token prediction function at each state. So it'll take in a sequence and then it'll return some probability distribution for the next token. So in this way, it's actually analogous to PDFA. The difference here is that it may have an abundant number of possible states. So what if we wanted to extract this a PDFA from this RNN? Well, there's actually an algorithm by Weiss et al. That we used to do this. And so we will look at 2 problems that this algorithm solves. Firstly, we no longer want to know whether a sequence is legal. So firstly, the Weiss algorithm uses the lstar internally, but it does some changes to it. So firstly, we don't want to know whether a sequence is legal because we're no longer using DFAs, we're using PDFAs. So it can easily be solved by swapping the columns for not whether some sequence is legal, but rather the next token probability. So if we look at the state reached by going lambda, which means just stopping at the start state, we can see that the end token probability denoted by a $sign is 0.3, and the probability of token A is 0.2. And so I hope you can recall the PDFA that we showed. Another problem was the unbounded number of states that the RNN has. So we would have an unbounded number of next token distributions. Weiss solved this by using a form of T equality. Here, 2 states are considered equal if their next token distributions are within T distance. So if you look at the state reached by stopping at the start state and reached by going sequence AA, we can see that the token A has 0.2 probability, and in AA it has 0.1. And the same for B, it has 1 distance between each other. So if we use a T equality of 0.15, the first state and the third state defined by the rows will be considered equal.
So prior to going into some of the findings that we have, and before going into our own research, we already knew that recurrent neural networks can successfully process sequential data. And so we had to attack it from that angle. We also knew that PDFAs have some similarity in form with language model RNNs. And so we could hope to find some interpretability in their relationship. And so we used the algorithms by Anglin and Weiss to extract them. And doing this, we found that through simplifying data structures enough, then PDFAs could, extracted from RNNs, could properly represent the intuitiveness of some network and what it's learning. And it also showed that the extraction could tell us something about the successfulness of the training of the recurrent neural network. We'll go through some quick notes as well. We also found early on that regular DFAs were too simple for complexity of traffic data and the probability of data increasing or decreasing. And we initially had this cyclic structure of the 24 hours of the day, which is this DFA. It's very simple on screen here, following the hours. And we realized that we had to find some different structure. So the dataset consisted of traffic data from 2016 all the way through 2020. We're mostly interested in these two far right columns here, which is the hour at some given day, for example, the 8th of January 2020, and the traffic volume at that given hour. These are cars passing through the junction back and forth. And so we pivoted the data set such that, and now the columns are the hours of the day. So 0 all the way to 23. And what's inside the columns are then the traffic volume at that given hour. So for example, we could look at Sunday. This is Sunday, the 12th of January. And at this day, you can go through all the hours and visualize that there's quite low traffic. This is a very busy junction in Bergen. We then changed this into ranges. So now all the numbers have disappeared. So the distribution is far easier to understand. And zeros here represent that there's less than 375 cars passing through the junction at that hour. And 1 represents that there are more. This is very close to the average rush hour traffic at this junction, which is around 394 cars. And of course, this cutoff range of 375 is a chosen cutoff range. We could have had a lower range, but we're interested in the rush hour traffic. So quickly, we'll recap the PDFAs that we're going to look at. So we'll keep in mind these two traffic ranges with the cutoff at 375, where zeros, which is here, is defined as low traffic, and 1 is defined as high traffic. And we'll also visualize these levels in the PDFA. You can look at this first level, we'll call it the 10th hour of the day, which has some end token probability and outgoing transitions. What we're interested in is using this PDFA to see if the RNN has predicted and learned properly. What is the chance that if there is low traffic at an hour T, what is also the chance that the low traffic will continue? Or what is also the chance that if there is high traffic at the hour T, what is the chance that the high traffic will continue? So we'll look at the first example here. We extracted January from all of these years to look at the PDFA. This is the 6th and 7th, 8th and 9th hour of the day. So the initial state at the top here is 6 o'clock in the morning on a January. And at 6 o'clock in the morning on January, there's a 50% chance of there being low traffic. And also there's almost a 50% chance of there being high traffic.
That the RNN has learned.
Yeah, so the RNN has learned this from the 6th hour. So this is the initial idea here. So also we want to see that if it has learned that there's a 50% chance of there being high traffic at 6 o'clock, what is also the chance that that traffic trend continues? And this will be the far left and far right trends here. So that you can see that the zeros represent low traffic. And as it continuously notices there's low traffic, it is learning that that probability will keep increasing. So 50% chance, 58% chance, 94% chance, and almost 100% chance of low traffic, given that the previous 3 hours were also low. So this poses the understandability that the PDFA is representing what the RNN learned. We would like to note that the last state here is just a dummy state. This just marks the end of the sequence. So this is just all days of the week in January. So we wanted to pose the question, what is different if you look at weekends or weekdays?
Yeah, and so we looked at Mondays, and here you can see that the RNN has learned there to be a 72% chance of there being high traffic. And given there was high traffic, so this means high traffic in the 6th hour, 6 o'clock. And so given that there was high traffic, it'll also predict there to be a very high chance that there's high traffic at 0 o'clock, at 7 o'clock, at 8 o'clock with 84%, and at 9 o'clock with 71%. So if you look at if there was low traffic at the 6th hour, 25% chance, it'll still predict there to be a high traffic at the 7th hour. So basically Mondays are very busy days. We would also like to note that given the way we've trained the data, we want all the end token probabilities to be 0 here, but it hasn't quite reached 0 at all.
In a comparison, you could look at Sundays. And so on Sunday, you'll assume, of course, that there's low traffic. We're not interested in actually the traffic of the day. We're more interested in what the PDFA is representing of the learnings of the recurrent neural network. And so, of course, you could imagine that there is very high chance that there is low traffic on a Sunday morning. But what happens here is the RNN is failing to learn based on the low amounts of ones in the data set, as there is very low traffic. And as the model is confused without enough training data, this properly represents that the PDFA will not learn properly based on what you give it. We added some more ranges as well. These are just rush hours, 6, 7, 8, and 9, all days in the week, all the years. Here we added another range, so we have low, medium, and high traffic. And what happens here is that the PDFA properly also represents, for example, 3 cutoff ranges. This is just to show that it's working. And so given zeros, it will continue this trend. As long as we kept the ranges few, it was still working.
Yeah, so we also added more hours, and we can see here that with more hours, you get sequences with where there's there's not that many training data for some sequences. And we can, it is reflected in the PDFA that the RNN hasn't managed to quite get enough data to learn the actual structure of the data set. So sometimes it misses some hours or adds some hours, which shows that something went wrong. We didn't give it enough data.
So to conclude, we're very happy that we successfully managed to extract a PDFA that gives some insight to what the RNN is actually learning and how it is learning it. Of course, we had to simplify the data enough for it to manage to properly create this tree structure. This tree structure is more or less for this traffic data. It would not be necessarily correct for other data sets. We also definitely found that this PDFA represents the properness of the training of the recurrent neural network. So further research into this area could be testing different data sets, visualizing whether PDFAs can properly represent the learnings of other trainings on other data sets. Yeah, so these are some of the papers that we used. And before we finish, we would like to let you know that there is now also open PhD positions at the University of Bergen. There are 2 of them. So if you'd like to apply, please contact Anna Ozaki. And considering her, she was a great help as a supervisor. So we'd just like to mention that. And yeah, if there are any questions, please let us know.